Welcome to your first lesson of chemical equilibrium. So, if you look at these beakers where there's water inside, you know that water goes from liquid phase to gas phase, and then we call it evaporation. Like in the ocean or the dams where the water evaporates to form clouds and then it rains again. So you know what is evaporation. Water goes from liquid phase to gas phase. Condensation is where water goes from gas phase into liquid phase. So that is when these gas-water molecules floating around here goes back into the water phase. Now let's look at this open system and a closed system. If it's a closed system, each molecule that goes into the gas phase must go back into the liquid phase at some stage. It cannot go out into the atmosphere and disappear. But if it's an open system, the water level would decrease because now the water is going from liquid evaporating into gas phase. And now the gas-water molecule can go out of the beaker and float away. So not all of the liquid phase going into gas phase can come back into the condensation part. So the level of the water will decrease. In a closed system, the level of the water would stay constant because each molecule that goes into gas phase must come back into condensation, into the liquid phase at some time. It cannot go out into the atmosphere and disappear. So very important. For an open system, the energy and the matter, the water gas molecule flowing away here, can move in and out. But for a closed system, only energy can move in and out. You can heat up the beaker or you can cool down the beaker. But the matter, the actual water gas molecule, cannot go out of the beaker. So that is a closed system. Very important that you know the difference between an open system and a closed system. And you of course know evaporation and condensation. Now this is an equilibrium system, equilibrium reaction. The water going from liquid phase to gas phase or from gas phase to liquid phase. Evaporation, condensation. This can form an equilibrium, and that is what these arrows indicate. So there is another example. These water molecules sitting here at the top can evaporate and float around and then come back by condensation. This is an equilibrium because it's a closed system. Here's another example. This water molecule doesn't like those. So it's saying, I'm sure glad they evaporated. And now they're saying, oh, we're back. They went back and condensated. So now this water molecule is saying, then I'm getting out of here. So now this one is going to evaporate again. This is equilibrium, a closed system. Now the water level will stay the same. So it will seem to you that nothing is happening. But something is happening. That is like a boy running on a treadmill. He is staying on one place. He's not moving anywhere. But something is happening. Just ask him. He's really tired, running, keeping pace with the treadmill. It's like a bowl like this, where the water is flowing in and water is flowing out. The water level stays the same. But remember now, this is equilibrium. Here is an example. Here are reactants and a product. The reaction went to completion. That means all of the reactants reacted and formed product molecules. If you say a reaction went to completion, it means that none of the reactants are left. All of them are gone. This is an irreversible reaction. You cannot just take the product back to reactants. It's done. They reacted and formed this product molecule. So this is an example of a reaction that went to completion. Now let's look at a reversible reaction. That is like the water. Water in liquid phase evaporates to form water in gas phase. But the water in gas phase can condensate to give you water in liquid phase again. That means this is reversible. The water can go to gas, the gas can go to liquid. Now, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. This is very important. That is the definition of equilibrium. The rate of the evaporation is equal to the rate of the condensation. And then you have equilibrium. Let's look at this example. You have H2 and I2 reacting to give you HI. Now, let's look at the forward reaction. H2 plus I2 gives you HI. That is the forward reaction. So in the beginning, the forward reaction would start, and the concentration and the rate of this forward reaction would decrease slowly. And then we also have the reverse reaction, because this sign means that this reaction can go forward and reverse. So now some of this product, HI, can go back to H2 and I2. So if you look at the reverse reaction, that rate would increase slowly, and then they will form equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction. Note that the amounts of reactants and products remain constant, just like in the beaker, where the level of the water remained constant. Here the amounts of reactants and products also remain constant. Now, very important. For equilibrium reactions, we want to calculate Kc, the equilibrium constant. This is just a way for us to measure equilibrium, but it's very important for you to know how to calculate it. So if we look at this general reaction, Kc would be the concentration of this product times the concentration of the other product, D, while C is to the power of whatever is standing in front of C, and D is to the power of whatever is standing in front of D. Then the same for the reactants, A and B. So, very important, Kc is the concentration of the products multiplied divided by the concentration of the reactants. And then you have to remember the exponent, which is the same as what is in front of that reactant. So this is measuring the ratio between products and reactants. So if the forward reaction is faster than the reverse reaction, the equilibrium will lie to the right, and Kc would be bigger than 1, because the concentration of the products would be bigger than the concentration of the reactants. If the equilibrium is lying towards the left side, it means that the reverse reaction is faster, and it means that Kc would be smaller than 1, because C and D has now lower concentrations because they are forming A and B. Let's do a quick example. For this reaction, write an expression for the equilibrium constant. Remember now, Kc is equal to the concentration of the products divided by the concentration of the reactants. So SO2 is the product to the power of 1, because there is just the number 1 there in front. And then the reagent is oxygen to the power of 1. Remember, we are excluding products and reactants that are pure liquid and pure solid. Sulfur is a pure solid, so we are excluding that in your Kc equation. Now we need to calculate Kc. So the concentration of SO2 is given to you. In the question it says 3 mole per cubic decimeter. And Kc is given to you, that is 6. So you need to calculate the concentration of the oxygen. So if you just rearrange your numbers, you'll get that the concentration of oxygen is 0.5 mole per cubic decimeter. Thank you.